So, and 23, problem number 23, the baseball player, normally they bat, but it says they're bunting. So the ball's going to hit the bat, boom, and the ball still moves away from the bat, but not like if they're swinging the bat, because when you swing the bat has momentum, and some of that momentum gets transferred to the ball, and the ball goes flying. So let's read this. So any physics problem, we're going to go through this process. And the process for solving most physics problems are kind of simple. We're going to read the problem first, all the way through. 2, we're going to draw the picture. Now, drawing the picture, basically what we're going to do is we're going to draw what's going on, because in physics, something's taking place. Physics is the study of natural phenomenon, and since all matter in the universe is in motion or one shape, form, or fashion or something, usually a physics problem involves something moving somewhere. So we like to draw the picture, and then we label the picture. And so the next step, once we draw the picture, is we kind of think about what we know. And that's usually where we label the picture. So I'm going to draw a picture of a bat and a ball, and then I'm going to list some information with it. But I'm going to list everything I know. Now, sometimes the stuff we know isn't what's in the book. The book's going to tell us a lot of stuff, but the stuff that we know isn't in the book. And sometimes the stuff that we know it, but it may not help us with this problem. But this is the process. Step number 4 is we need to list what we need to know. Usually in a physics homework problem, they want you to find something. Okay? Now this usually involves some sort of equation. So if we list what we know, when we list what we know, there's going to be a bunch of variables here. Like velocity, mass. I'm sorry, I ran out of room on the screen. That word's a variable, but mass or velocity or time. And we're going to list all that stuff. And when we go to pick the equation, guess what? The equation is going to have these variables in it. And it's also going to, what we need to know is also a variable too. So those 3 parts are kind of connected, but the equation we picked is based on what we have and what we need to know. So what we know, what we need to know is how we pick the equation. And then usually once we pick the equation, then we solve. And then usually for number 7, we kind of double check or do like a common sense double check and see if the answer makes sense. All right, so we're going to talk about baseball bat and a ball, and we're going to, at some point in time, we're going to make some calculations. If I calculate that ball is traveling faster than the speed of light, I made a mistake somewhere. All right, if the amount of force that hits that ball seems unreasonable, then maybe I made a mistake. And it doesn't matter if I entered the answer in the calculator, I could still hit the wrong button, right? So that's why every problem, no matter what problem I pick out of this book, no matter which one, Mr. Adams every time will go through this process. Okay? And I think that's the challenge when you guys try to do this homework at home. I've taught you a bunch of things, and we're on the 3rd or 4th section, and what are there, 6 equations so far? And if I don't go through this process and I try to pick one equation and I pick the wrong one, then I find out it doesn't work. And so you might find yourself in a situation where you're trying to find the answer and you go through 3 or 4 equations and none of them work. And I can see where somebody might get discouraged and give up. That's why it's so important that we find and list all the variables and the information we know and then try to tie it into what we need to know. That's how you narrow it down and pick the one equation. Okay? So now let's read this and then we'll draw the picture. When bunting, a baseball player uses the bat to change both the speed and direction of a baseball. Will the magnitude, and so these are the options that they give us. A, will the magnitude of the change in momentum of the baseball before and after the bunt be greater than the magnitude of the momentum of the baseball, either before or after? Part 2, or option number 2, equal to the difference between the magnitudes of momentum of the baseball before and after the bunt. Or 3, equal to the sum of the magnitudes of the momentum of the baseball before and after the bunt. And then you have to explain why. Yes, do you have a question?
No, it's 3.
Yeah, well, we might think that it's 3, but to be honest with you, how do we say why? Huh? Yeah, the momentum is conserved, but we got to prove it. Quickly. Quickly, yes.
In the equation that is like the conservation of momentum or mass or whatever, p sub 1 minus parentheses negative p sub 2 is equal to p1 plus p2.
Okay, good. You're getting a little ahead of me, but you're good. What I was going to say was, we know that the answer is the third option, but when we go to prove it, what it boils down to is we're just going to have some numbers and crank through the equations and solve. So momentum is conserved, like she said, right? And she's saying, okay, we have this equation, and we're going to pick it up. And that they're right, but we want to go through this process every time. So the first thing is I've read the problem. Number 2 is I'm going to draw the picture. So this is my little bat. All right, that's the bat. All right, and then the ball is coming in here, and it's going to come with a certain velocity, and this ball has a mass, and this has a velocity, and it's the initial velocity, so we call it V0. It's going to make contact with the bat. Okay, so this is like the first phase. When it gets here, and it makes contact with my bat, after it makes contact with the bat, then my ball, whose mass is still the same, but now my final velocity, which is a vector, is going in this direction. Okay? That's the picture. Ball comes in, hits the bat, and the ball collides, and then the ball goes the other way. I don't have any numbers yet, and that's kind of where she was hitting around to. Okay? So now, what do we know? We know what I've just kind of drawn. Is there anything that Mr. Adams has left out? What do we need to know? Well, option number 3 kind of proves that the momentum is conserved, right? And we need to prove that with some numbers. So we're looking at basically the change in momentum, right? So what we need to know, the question that I have here, what I need to know, so we've gone through and listed what we've known, we've drawn the picture, and we get to need to know. What I need to know is what is the change in momentum, because that's really what the question is asking. Right? Let me read it again so you guys know what we're talking about. It says, will the magnitude of the change in momentum, delta P, what does the delta stand for? Change. What does the P stand for? Momentum. Of the change in momentum of the baseball before and after the bunt, will it be, and then it gives us 3 options. Okay? And we said number 3 seems right. Now the reason we said number 3 seems right is because we know 1 isn't correct, and we know 2 isn't correct. That's kind of easy to prove. But proving that 3 is correct is going to take us plugging in some numbers in an equation. Okay? Well, that's part A. So we're going to not answer that right away, although 3 is correct. But part B of the question says this. The baseball has a mass of 16 kilograms, or 0.16 kilograms. And I'm going to write this off to the side. The mass of the baseball is 0.16 kilograms. So the baseball has a mass of 0.16 kilograms. Its speed before and after the bunt are relatively, before it's 15 meters per second, and after negative 10 meters per second. I suppose that Mr. Adams wanted to be real picky about it. What did the book say that really technically isn't correct? Well, they said speed. Okay, they said speed, 10 and 15. What did Mr. Adams write down?
Velocity.
I wrote down velocity. I said 10 and negative, or 15 and negative 10. Now, where did I get that from? kind of made a mistake. I've taught this problem once or twice. If the initial speed is 15, does that have a direction? No. Can I assign a direction to it? So when I assign a direction to it, that's the direction is either positive or negative, right? So I'm going to assign this a value. So we know it's 15, but I'm going to assign a positive. In other words, when the ball's going this way, it's going to be positive, and when the ball's going this way, I'm going to assign it a negative direction. All right? And I could do that. Now, I purposefully did it backwards, because normally this way is positive and this way is negative. And that's okay. The numbers would work out the same either way. What the important thing is whatever one is positive, if this direction is positive, this direction is negative. If I made this direction negative, what would this direction be? The opposite, positive, okay? Now the reason I do that is we're going to get an answer, and the magnitude will probably be the same, but maybe the sign is different. I don't know. We'll see when we print through. So I have a mass, I have an initial velocity, and a final velocity. And it says, what is the change in momentum of the baseball? Because that's really our answer to part A. So now, we've listed what we know, and then we've listed what we need to know. What's the next step?
Find an equation.
Find an equation. Now, conveniently for you, in your textbook, on page 212, they've listed all the equations for chapter 6. Now, this is kind of cheating, but look on that. What do you notice? Well, the first thing that I notice is that momentum is equal to mass times velocity. And momentum is a vector, and so is velocity. But we're talking about the change in momentum. So how do you get the change in momentum? Well, if you go down a little bit for 6.5, see the baseball player? How did they rewrite that? They said the mass times the velocity minus the mass times the final velocity, right? Now, I'm also a mathematician, so to make my life a little easier, what Mr. Adams is going to do is I'm going to factor out the mass, because it's the same mass. Does the mass of the baseball change at all? No. Sure doesn't. So now I've got the mass, which is 0.16, right? And then I've got negative 10 minus 15. So when I do that, I have a change in momentum of 0.16 minus 10 minus 15. Now, did anybody do this with the orientation differently? In other words, the first number was negative, like this was negative and this was positive. Did anybody do it that way? Okay. Well, I'm not going to waste time and do it the other way. The numbers and everything will work out. It'll match. Okay. It'll match in the sense that our final answer will determine what happened. So now my change in momentum, if you crank through all the math, what is negative 10 and negative 15?
Negative 25.
Negative 25. And then when I multiply that by 0.16, what do you get? It's like 588. Somebody do that on their calculator. I guess I have a calculator right here, actually.
Negative 4.
Is it? Oh, yeah. Okay, yeah, that's right. I'm thinking of a different problem. All right, so if I say 0.16 times negative 25, I get negative 4. So that's the answer. What did the back of the book say?
4. 1.6 times 10 squared. No, that's second part.
Well, yeah, wait.
We are on the second part.
Well, actually, it's the third part, and we're not on the third part yet. Listen to the question I'm asking you. What did the back of the book say for this one? Positive 4, right? Now, the reason it has a positive 4 is because they did the orientation differently than the way Mr. Adams did. But the magnitude is 4, right? Now, what does the negative or positive represent? Which way it's going, right? So, because Mr. Adams made going this way positive, right? Did my voice crack?
No, it was just
No,
something
it's
really
like-
funny.
You're talking. Yesterday it was this really weird low thing, and now it's like.
Like
I
all water.
cannot. My sinuses are all stuffy. I literally cannot talk and breathe at the same time. But thanks for laughing at me.
You're welcome.
So, anyways, because I chose positive to go this way, the change in momentum is opposing that, right? So the change in momentum is this way, away from the back. Now, if I would have set up my orientation differently, I would get the same answer in the back. The magnitude would be the same, which is 4. But if I set it up differently, which way would it go? This way, still away from the back, right? Let me write that down so you see what I'm saying. We have 4 here, but the back of the book they said that this direction is positive and this direction is negative. Well, if that's the case, then their change in momentum would have been positive 10, right? And then minus 15. Times the 0.16, right? Which was equal to positive 4. That's what the back of the book said, right? Well, 4 is positive, but what direction? This direction. Mr. Adams set it up differently, but what direction? This direction. Both of them away from the back. Does that make sense? Okay, good. That's the second part. The third part is part C. What is the average force? So when it says, what is the average force that the ball puts on the bat or the bat puts on the ball? Well, they want the force. Go back to page 212. 212 says that we can find that force by calculating the change in momentum over the change in time. Now, the one thing I got a little excited, start writing down the numbers. The one thing I forgot to mention is that the textbook said that the time that this collision between the ball and bat takes place is 0.025, right? So we have 4, or in our case, negative 4, over 0.025. And that is it 1,600? Negative 1,600. So it'd be 1.6 times 10 to the 2 newtons, right? Now that seems kind of high, but anybody that's played baseball, you know, that doesn't seem that high. 1,600 newtons of force seems pretty reasonable. Would anybody in here like to put their fingers between the bat and the ball? No. It'd be very painful. That's a lot of force. And that's what the answer in the back of the book says. Alright? So now, technically, for this one it said magnitude. So remember that the magnitude is this number. Right? And it's the same with the force. If I were to talk about the magnitude of force, it would be that number, the 1.6. Does that make sense?
Yes.